Earth's crust moves at roughly the speed your fingernails grow, and yet that slow creep can suddenly release energy equivalent to thousands of nuclear bombs in less than a minute. Those violent spikes on a seismograph, those eerie sounds that seem to come from nowhere, those mysterious lights flickering in the sky before a quake, or the strange rogue wave that appears from a calm ocean like a wall of water. It's tempting to treat these as glitches in Earth's matrix, spooky exceptions, fun trivia, curiosities for late-night Wikipedia dives. But if we stop at weird, we miss the real power of these phenomena. Because hidden in every glitch is a signal, information, clues about how a planet-sized machine actually runs, where it fails, and how it warns us before it breaks something important, like a city. In this chapter, we're going to ask a simple question with very non-simple consequences. Why do these mysteries matter so much to science, to safety, and to our future on a changing Earth? Let's start with danger. Imagine you're trying to debug a gigantic, badly documented piece of software. The code base is 4.5 billion years old. No one wrote comments, the hardware is a spinning ball of molten rock and metal, and every now and then, the program crashes catastrophically. Earthquakes, volcanic eruptions, tsunamis, megastorms. The glitches we talk about, strange lights, infrasound booms, unexplained animal behavior, odd electrical disturbances are like obscure error messages in that code. They're not the main event, they're side effects. But if we can decode them, they become early warnings. Take earthquakes. Right now, we cannot predict the exact time, location, and magnitude of a quake in a deterministic way. We can say where they're likely to happen, along plate boundaries like the San Andreas Fault, or subduction zones like the one off Japan, but not, there will be a magnitude 7.1 here, next Tuesday at 4:17 p.m. However, some of the alleged glitches around quakes are really attempts by the planet to telegraph what's about to happen. For example, there are reports, some anecdotal, some systematically collected, of unusual electromagnetic signals before earthquakes, changes in the ionosphere, which is the electrified upper layer of the atmosphere 60 to 1,000 kilometers above us, odd ultra-low frequency radio noise, local disturbances in the electric field near the ground. There are also credible observations of earthquake lights, luminous glows, pillars, or flashes in the sky during or just before major quakes, documented in modern videos and photographs in places like Japan, Italy, and Mexico. Each of these is like a partial error code thrown by the Earth's crust. One leading hypothesis links these phenomena to what happens when you stress rocks just below the surface. As tectonic plates grind, compress, and bend, the rocks in the crust accumulate mechanical stress. On a tiny scale, that stress creates microcracks, little fractures forming and snapping shut. Certain types of rock, especially those containing quartz and other minerals with specific crystal structures, can generate electric charges when they're deformed. This is related to the piezoelectric effect, the same principle that lets a quartz crystal in a watch generate a stable electric signal when it's squeezed. Under intense stress, the density of these cracks and defects increases. The theory is that this can lead to localized charge separation, a bit like rubbing a balloon and building up static electricity, but distributed through cubic kilometers of rock. Those charges can migrate, building up electrical potentials on the surface and even radiating electromagnetic waves at very low frequencies. In some experiments, stressed rocks emit bursts of infrared light or free ions into the air. If enough of this charge reaches the atmosphere, it can perturb the local electric field and potentially trigger small-scale plasma discharges. These might manifest as faint glows or streaks of light near faults, what observers call earthquake lights. To be clear, this is still an area of active research. Not every quake has documented lights. Not every light in the sky before a quake is a rock-generated plasma show. But here's the key point. Whether or not a specific mechanism turns out to be right, following these weird signals forces us to measure the crust, the atmosphere, and the electromagnetic environment with much greater precision. When Japan deploys dense seismometer arrays and ionospheric monitors, or when satellites like Demeter and Swarm track tiny fluctuations in Earth's magnetic and electric fields, they're not just collecting abstract data. They're trying to answer, Can we reliably detect a pattern before a fault ruptures? Can one of these glitches be turned into an operational forecast? Even if the answer is only sometimes, only probabilistically, that still matters. Improving early warning by even tens of seconds can save thousands of lives by automatically shutting down gas lines, stopping trains, and sounding alarms. So a mysterious flash of light in the sky is not just cool footage. It might be the visible symptom of a planet-scale fracture forming and a potential handle we can grab for prediction. The same logic applies to volcanoes, tsunamis, and extreme weather. Volcanoes often have their own glitch catalog before they erupt. Harmonic tremor, a continuous vibration in the ground like a low musical note, changes in gas emissions, especially sulfur dioxide and carbon dioxide, ground deformation as magma pushes upward, even subtle shifts in local gravity as dense magma moves around below. Each of these signals is indirect. No one sensor says eruption in 48 hours category 3. Instead, volcanologists build multi-parameter models. They feed in seismic noise, tilt measurements, gas chemistry, satellite imaging of the thermal signature, and more. Together, these are used to calculate eruption probabilities and issue color-coded alerts. The weird behaviors we notice, like a crater lake abruptly changing color or temperature, or a volcano rumbling with infrasound too low for human ears to hear, are the human-facing edge of a very deep physical process. Magma rising, pressure changing, gas exsolving, rock fracturing. Studying those glitches has led to concrete tools like the Volcanic Explosivity Index and real-time hazard maps that governments now use to decide when to evacuate. Tsunamis tell a similar story. The most obvious glitch is the ocean suddenly withdrawing from a shoreline, exposing the seafloor where there should be waves. That's not magic. It's the trough of a long wavelength wave passing by, the ocean drawing back before the crest arrives. Historically, people didn't know what that meant. Today, that retreat is a well-understood warning sign, powerful enough that simple educational campaigns, if the sea suddenly goes out far and fast, run uphill immediately, have saved lives. But scientists go further upstream in the causal chain. Deep ocean pressure sensors anchored to the seafloor measure changes in water column height as small as a few centimeters. A tsunami in the deep ocean may only be a gentle undulation, but those instruments detect it, send data to buoys at the surface and out to satellites. Global monitoring networks ingest those subtle blips and feed them into numerical models of wave propagation across entire ocean basins. So what looks like a glitch to the naked eye is actually the surface-level manifestation of a tightly integrated system of physics, sensors, models, and decisions. Earth's glitches don't just predict danger, they also expose how deeply interconnected all the layers of our planet are. Consider thunderstorms. Everyone's seen lightning, but high above the clouds, in the thin air of the mesosphere and lower ionosphere, there are stranger, fainter flashes called sprites, jets, and elves, emissions of light and very low-frequency perturbations due to electromagnetic pulse sources, because scientists can't resist a good acronym. For a long time, pilots and astronauts reported these red, jellyfish-like flashes leaping upward from storms, and they weren't taken very seriously. They sounded like UFO stories. Only in the 1990s were sprites conclusively captured on camera and studied in detail. Now, we know they're gigantic electrical discharges triggered by powerful lightning strokes. A single sprite can extend 50 to 90 kilometers upward, briefly altering the chemistry and conductivity of a region of the upper atmosphere hundreds of kilometers across. Why does that matter? Because the ionosphere is not just some decorative aurora canvas, it's a key part of the global electric circuit, a planet-wide system where thunderstorms pump charge upward and a very slight continuous current flows between the ionosphere and the ground, on the order of a few picoamperes per square meter. This global circuit influences how radio waves propagate, how cosmic rays interact with our atmosphere, and how energy from space weather, like solar storms, couples into our environment. By investigating these once dismissed glitches above storms, scientists had to build better high-speed cameras, lightning detection networks, and atmospheric models. In doing so, they linked weather we experience on the ground to electromagnetic dynamics 80 kilometers overhead. The message is consistent. Odd phenomena are often bridges connecting different layers of Earth's system: crust to atmosphere, ocean to solid Earth, weather to space. These glitches also matter for a reason that operates on a very different timescale. Understanding how Earth changes over deep time, and how our current moment fits into that story. Some of the mysteries we notice today are actually echoes of long-term cycles. Others are hints of transitions still underway. Take Earth's magnetic field. It's generated by the geodynamo, the motion of electrically conducting liquid iron in the outer core, roughly 3,000 kilometers beneath your feet. This dynamo produces the magnetosphere, the invisible shield that deflects most of the charged particles streaming from the sun. But the magnetic field isn't stable, it wanders, it weakens and strengthens. Occasionally, it flips entirely, north becomes south, and south becomes north. These events are called geomagnetic reversals, and they've happened irregularly throughout Earth's history, with an average spacing of a few 100,000 years. Right now, we're in what appears to be a long-term weakening phase of the field, especially over a region called the South Atlantic Anomaly. Satellites passing through this zone experience higher radiation levels because the field there is unusually weak and dips closer to Earth's surface. It's a glitch in the otherwise smooth magnetic shield. Why obsess over that? Because rocks on the seafloor, frozen lava flows, and sediment cores all record the magnetic field direction at the time they formed. They contain tiny magnetic minerals that line up with the prevailing field like microscopic compass needles and then get locked in place as the rock solidifies. By reading these records, a field called paleomagnetism, we reconstruct a detailed timeline of field reversals and intensity variations going back tens of millions of years. Those magnetic glitches in ancient rocks tell us not only about the history of the geodynamo, but also about plate motions, seafloor spreading rates, and even past radiation environments at Earth's surface. They calibrate our models of how the core evolves and how heat flows from the deep interior outwards, driving mantle convection and plate tectonics. Just like a weird error in a computer's power supply can hint at both the CPU and the cooling system, a strange magnetic anomaly on Earth connects the core, the mantle, the crust, and the life on the surface that depends on radiation shielding. Climate science has its own category of glitches. When scientists drilled kilometers-deep ice cores in Greenland and Antarctica, they discovered layers like tree rings, each one representing a year of snowfall compressed into ice. Trapped in those layers are tiny bubbles of ancient atmosphere and isotopic ratios of oxygen and hydrogen that encode past temperatures. When you plot those data over the last 800,000 years, you see a pattern. Long ice ages punctuated by brief warm periods like the one we're in now. These are paced by predictable changes in Earth's orbit and axial tilt, called Milankovitch cycles, which alter how sunlight is distributed over the planet. But superimposed on those broad swings are abrupt events that look, frankly, glitchy. Periods where temperatures in Greenland jumped by 5 to 8 degrees Celsius in just a few decades, or the so-called Younger Dryas, a sudden return to near-glacial conditions about 12,900 years ago, after the planet had started warming out of the last ice age. These rapid changes are not fully explained by the slow orbital cycles. They hint at tipping points and feedbacks within the climate system, shifts in ocean circulation, changes in ice sheet dynamics, or massive pulses of fresh water disrupting the Atlantic meridional overturning circulation, the ocean conveyor belt that moves heat from the tropics to the poles. By treating these climate glitches as serious puzzles, scientists have built increasingly sophisticated Earth system models that couple atmosphere, ocean, ice, biosphere, and carbon cycle. Those models are the same ones we now use to project future warming under different greenhouse gas scenarios. We've been looking at glitches as warnings and clues, but there's another way to see them, as invitations to question whether the matrix we think we understand is even the right one at all.